Okay, for people joining this live stream, sorry, we're starting slightly late here. This is the design review about, well, what are currently called compiled layers for the neural net framework. They probably won't stay as compiled layers for more than a few minutes here, but we'll see. All right, so let's get an understanding of what this is. This is, oh boy, do we have people from the compiler group here?
No, but I'm not sure we would need them.
Okay, but I'm not prepared to have a discussion about function compile without them.
Oh, I mean, we're not really going to discuss the function compile. We're going to discuss everything that is around it. Yeah, this
okay,
we know.
Have you looked at Christopher's new tooling for the compiler?
I did not.
Then I don't think we're going to be able to have this conversation.
I mean, this is, you know, everything I put in this notebook, there's nothing about function compile.
Except at the very beginning.
Except at the very beginning, because okay. the everything is about, you know, the backward function, the you know, I mean, there's a bunch of things to talk about how to specify the name of the input ports, the output ports, like.
Okay, so let me just understand what this is.
Can be a black box.
Hold on. This is or is not using our compiler?
It is. It is definitely using a compiler, but it could be a black box for us. Like
but it's generating LLVM code that is then being run. Is that correct?
Yes. Yes.
Okay. You need to use this tooling that Christopher has been working on.
Yeah, we were talking about that with Matteo. We haven't looked at it, but like for us, if there's a better packaging of this, is great, but it doesn't really change everything else. It's so the idea is to piggyback on whatever.
Okay, but so to what extent is this compiling to MXNet code, and to what extent is it compiling to raw LLVM?
It's not compiling at all to MXNet code. So there's two things: that net function, that this one is meant to be kind of converted not to MXNet but to our layer on top of MXNet.
So wait. So this is running an LLVM plus our RTL. Is that correct?
I don't know.
Yes.
RTL. Yes. Oh yeah. Okay. Yes.
Runtime library.
So yeah. So this is not net function, right? Net function is a bit more the higher level thing that will try to create a graph, that will try to convert things to MXNet. This is the lower level stuff that we give code. It converts it to with function compile to LLVM and whatever. And we'll use it. Won't convert it won't convert that to MXNet. It will just run.
Okay, so this has all been changed. Okay.
Sure.
That's all been changed. So it's no point in designing something around this.
That doesn't change anything.
But those things are only supposed to be arguments inside our function. So even if the form of the expression changes, you know, if the representation changes, for us they are still arguments to.
Right. I thought I'd asked this last time to make sure that if you're using the compiler, you have people from. Okay, whatever. I will look at this.
It just doesn't matter. So I mean,
all right. So as far as you're concerned, okay. So you're telling me that function could as well just be a piece of top-level code. Is that correct?
No, absolutely not.
So
because
then why?
It needs thread safety. That's just a technical thing. Is that MXNet starts many thread, right? And our regular code is not thread safe. So if you put that into MXNet, naively we thought we could do that at some point. It just mess around.
Have you talked to anybody about what it would take to make a version? Because it just needs a separate kernel, right? You can't do it threaded into the existing kernel, but you could do it as a separate kernel thread.
It was not practical. It was not practical. This we definitely talked. It was at the time it was Tadi and Sebastian that were on that, and this is not practical. But the great thing is that
why
is thread safe.
Why?
I don't know why.
Okay, so let me explain what I think they thought, and I think they were wrong. Okay, now, okay, they were not imagining that you could start a whole separate kernel to live in that thread. I think you can.
But I think it's starting thread all the time and killing thread all the time. I think it's like hundreds of threads. I mean, it's super complicated machine.
How many threads? Well, how many threads?
It depends. It depends what the form of the network is, but it's in general there's no limit.
Okay, that's not useful to me. Tell me the average number of threads running on a typical CPU.
the average number of threads running on a typical CPU, it's
okay. Do I need to run this and find out? My guess is that you're talking about on the order of, because it's not, doesn't do you much good to run more threads than you have cores.
Sure, but
Okay, so I don't think this is a good. Okay, listen. There are several things that have changed. First of all, we now have forking, which means the cost to start a kernel is much lower. Okay, and it doesn't take additional memory to have an additional kernel started. I think we can do this.
Okay, this is something that has been. I mean, Sebastian and Tali have been working a lot on that, talking with everyone. I mean, okay, there's maybe some new stuff, but one thing that is sure that this works. The compile stuff is
well. The compiler works if the compiled stuff works if the compiler works, but the compiler doesn't work well yet.
That's true. That's true.
So we're not going to be able to do stuff. I mean, the compiler right now has a minimum runtime of 15 seconds, roughly, which is fine if you're compiling something once. It is not applicable to just-in-time compilation.
Yeah, which we won't do in that case. But I mean, actually, that would be nice in some case. Yeah.
Well, but so you're saying this is something where you would compile it when it is created, when it's put in the neural net repository, and then it is not compiled again. Is that right?
No, actually, I think you're right. It has to be compiled.
Okay, but that's not going to work. It's simply not going to work.
Per session, Stephen, it's one per session.
It's not going to work. It's not going to work.
Yeah, it's true. When you load your network, it compiles.
When you load the network, it has to recompile.
Okay. Why?
Yeah.
Why?
Because it's the same reason why when you load a compiled function from a WXF file, it recompiles it.
Why?
Maybe the technical way.
Why? I think you're wrong. I think what's happening there is it doesn't know the architecture that you're on, and you are making the mistake of thinking that you can't have essentially a fat binary that deals with multiple architectures, which we can have.
It probably doesn't compile to that fat binary right now. I don't know.
Well, but that's why you needed to learn about the new tooling, isn't it? Right?
But is this new tool just only wrapping the existing compiler, or is it a completely separate thing?
It is tearing apart a bunch of stuff in the compiler that wasn't well designed and putting new stuff in there instead.
Okay, but
all right. Well, that's good. That's good. If I mean, it's true. Technically, I don't see a reason why it couldn't just keep the LLVM and not have to recompile every time. That doesn't make sense.
Right. Doesn't make sense.
So we'll probably find a way.
Okay. So let's walk through the use cases again. Okay. So I want to walk through what you're actually talking about. First point is there are networks that involve raw code that is not represented by our existing layers and is not implemented by the essentially MXNet interpreter, right? Those are the things you want here. Things that are raw code that is not available in the essentially MXNet runtime library. Is that correct?
Or that we don't have a representation.
No, that's not correct. You've got a different mechanism for dealing with other things that are in the MXNet layer, but not at our top level layer, correct?
No, this is internal. This is not.
Okay, what was the thing you were showing me with net function?
So net function is converting code to our framework. So it's actually constructing a net graph underneath and converging everything in our layers. And
okay, so but I thought there was a mechanism which we talked about to access raw MXNet functionality, like an assembly language.
Yes, but it's undocumented. It's called MX layer. It's internal.
Okay, why is it undocumented?
Because we never thought about documenting it. It's pretty ugly. You have to deal with a lot of MXNet internals.
Okay, so my question is this. The kind of wrapping that we have of that low level, layer, right? Can we generalize that to other? I mean, is it the case that there are other, or is it the case that other things have just been sort of hacked into MXNet and they have different weird designs and they don't follow, they're not consistent with the kind of flow for net graph and so on? Is that what the situation is, or what?
Well, MXNet also has graphs, and they have nodes.
Okay, can you answer the question? Can you answer the question? What I'm asking is it the case that there are things in MXNet that are design compatible with what we have, but simply haven't been implemented? Or is the stuff that we don't have design incompatible with what we have?
I think it's more the second. There's a bit of the first thing. It's more the second. Our thing is higher level than MXNet. It works a bit differently. For example, the weights are inside the layer, not outside. Now there's a little bit of stuff that are in MXNet that we don't have yet. And for example, more imperative type programming. And I think that's what you were thinking about when talking about net function. Eventually, we want net function to be able to understand
so you've got a path.
Complex code.
Right, but yes. So what is your path there? Because what you're describing is the net function right now is compiling to our existing layers. That's what you're saying.
Yes,
right?
yes.
Okay. You think that there's a possibility that net function might be able to directly compile to MXNet stuff or other frameworks.
For example, with like imperative programming type network. So things that don't fit into a graph. You know, you have a loop, you have statements, you have
I get it. Yeah. Okay, so what will be involved? Okay, to do that, are you imagining, because one possibility is that you could take the compiler framework with all its type specifications and so on, and emit as the code generator some different kind of code than LLVM. Right?
I don't.
Because,
well, yes. They have the, they said that eventually we'll be able to compile to CUDA, which is awesome for us.
What will be able to compile to CUDA?
Our compiler.
Yes.
Our compiler, but that's an endgame for us.
But I don't understand. Okay, I don't understand. You've got two paths here. You've got one path where you say you're trying to compile things. Okay, there's three different targets. Our top-level layers, MXNet, and LLVM and other low-level direct executables.
Yes.
Is that correct?
Yes.
Yes.
Okay.
Yes.
So what you have here is a design for wrapping for neural net use directly executable things. Is that correct?
Yes.
Okay.
And that's lower level than net function. Eventually, I expect net function to be able to handle a bit everything automatically.
Okay, so then the concept would be that net function, if it encounters something that can be implemented as a compiled layer, it would do the compilation and implement it as that.
Exactly.
Is that correct?
Exactly. Yeah. It will do the best each time. If you can go to MXNet, go to MXNet, and so on.
Okay. So now the next question is the actual use of this, given the current state of the compiler, right? So that depends on, in my view, being able to have one of several things. There clearly is architecture dependence to the LLVM files, right? Actually, maybe there isn't to the LLVM itself. There may not be. It may be just a last level of LLVM processing that requires, which is why you need to know about this new tooling, right? Because that's what contains the, okay. So one possible workflow and use case is you do the compilation once and for all. It's in the neural net repository. You download it, and there are two possible flows there. One is you download something which is at the level before specification for a particular architecture, and that specification happens quickly. I don't know whether that's possible. Or two, because the whole type analysis layer cannot be run in real time at this point. Am I making sense?
Yep.
Okay, so possibility number two is you store, well, there are actually two other possibilities. One that I don't really favor is that you download a fat binary. I don't think that's a good idea. I think they'll get big, and I think it's a bad idea. The other idea is that there's an interlock with the neural net repository, which I think is doable, where you simply request the appropriate binary based on your architecture.
I mean, it's not just a repository, right? It's anyone that creates a network and save them somewhere and re-upload them. I think it should.
No. I'm saying that's not realistic, right? We can't do at this time. We will be able to do it, but at this time we cannot do compilation on demand. So that is not a workflow that is interesting.
Why?
But the whole idea is that
I just told you why. I just told you why. It's too slow.
Is that it's platform independent. So
right.
once
Okay.
you
So
have it,
if we knew about the right tooling, we would be able to answer this question of whether there is a thing you can store, which there probably is.
Yeah, I think so. I mean, that's the whole point of an LVM, to have something that can be run on the machine. So I don't see. I mean, it's true that I've been surprised that if you copy paste the compile code function here, it actually compiling again. But I don't see any
Ethan
technical...
on our live stream is saying we should throw out MXNet and use PyTorch instead.
Okay.
Well, it's the third time, and we've already changed 3 times what underlying framework we're using. So it's not obvious we couldn't change again. And we certainly have thought about supporting additional frameworks. It would be interesting to know what would be involved in doing that.
A lot of work.
Yeah. I'm not sure.
Why?
So did just why?
Yeah, why?
Okay. Well, for start, we will have to re-implement all the layers in a new.
Well, of course. But that's the question is: are those layers compatibly implemented in different frameworks? Presumably, Onyx is an attempt to standardize what happens.
Yes,
right?
Of course.
So my question is, yeah, go ahead.
Well, it's not impossible. Like, we can absolutely re-implement everything we have in PyTorch, but as I said before, it's a lot of work.
But,
and it's
but
not
what
just
is the
layers.
point? That's the big
Yeah,
question.
what's the point? I mean, what happened when we originally picked MXNet after we had used, what were the 3 things we used before it? I can't even remember.
Well, it was Torch,
Keras,
and Cafe.
Torch. Yeah, Cafe,
Torch.
Keras, Torch. Yeah, I think.
Not Keras, but yeah.
Oh, we didn't use that. Okay.
No.
But those were very, very early days, and the framework was forming, so switching was not a very big deal because there wasn't much. Now
it was a big deal. It took months.
Okay,
but,
now it will take way more. Like
okay,
now,
but I'm not really believing this. But it doesn't really matter. I don't think it matters because I think that the low-level implementation layer is not the most important thing, and in the end, that low-level layer will just go away. And it will be replaced by, going essentially from net function down to whatever the final, whatever the final compiled code is. And, in a few years, that's how it will work. So I'm not that concerned.
Cool. Should we go over the design? I think the compiled
by the way, for
function,
people on the live stream, the reason we're not using those things is because they were slower. I mean, when we benchmarked them, they were simply slower. Okay, so let's.
And there was a bunch of reasons for it. It was working everywhere. C++ library.
Right.
And it was kind of alone. TensorFlow didn't exist when we started, on MXNet.
No, it did exist. It was just bad.
It was not yet. When we started.
Oh, when we started, obviously.
Yeah,
it didn't
6
exist.
months in, it appeared, but it wasn't working on Mac.
Yeah. Anyway.
All right. So in a design, so whatever compile thing we use.
I don't believe in this. I'm sorry. This is stupid. No way. What are you doing here? What is it? What is this tuple thing?
This is to specify currently, not currently, that's a current plan to have several arguments in a list.
Okay. Talk to the compiler people about this.
Yes, we did. We talked.
Okay. Why isn't there anybody here from that group? As I've said 5 times.
Because we talked about them a lot, and we are.
Okay. It's not gonna fly. That's not gonna fly.
We don't know the exact design for that. They just told us they will provide a way to create a function that have different type in the same list. Because currently it's one argument, one type. Right? That can be a scalar. It can be an array. But
okay, is this an alternatives? Is this alternatives or is this?
No. It's a list. It's a list.
It's a heterogeneous. It's a struct, basically. It's a struct, basically.
Yes. It's a list, and then you have here you have in that example array of rank 1 and array of rank 3.
All right, let's take a look here. What you're doing here. All right.
So.
All right. So your idea here is that you will simply have a compiled layer that takes this function inside. Now remember that function, I could replace that function with a top-level function, right? Now, you don't know how to implement that, but conceptually I could replace it with that. That is, all the thing does is it takes certain arguments and returns a value, correct?
No, there's information about type and about rank, and this we use as well. They're useful.
Okay, hold on. So you are getting meta information from that compiled code function, which you believe you do not have from an ordinary function. Again, we needed the compiler people and their tooling discussion, because I don't think that's correct. I think we do have mechanisms to get that kind of type information for just a regular plain top-level runnable function.
That would be
so that's first thing.
Shapes, you will never have it until you define it somewhere, or rank until you define it somewhere.
Well, wait a minute. If the function takes something of a definite shape, then it will be specified. If it takes something of an indefinite shape, then it will presumably parameterize what shape it can take. Right? So first pin here is that isn't right. There should be a wrapper that will work with an ordinary function, not a compiled function here. But we'll go past that, right? What information exactly are you using?
You know what? I think we're bordering on net function here. Net function indeed can work with anything, and we'll try to make it automated. This is a low-level thing. That's why I wrote the first thing, low-level thing to convert WL code into function compile. It's not meant to be the big, so it's a low-level stuff. You just work with compile code function. It's useful right now a bit more for experts, and it's going to be used inside net function. That is a real the big guy. So that's our idea.
I understand. I'm trying to understand this design. Okay.
Yeah. Okay.
So as far as I'm concerned, the inside of compiled layer is a function that has two attributes. It takes values and it takes inputs and returns a value.
Yeah.
Thing number one, just like an ordinary function. And second thing, it has meta information that you can extract about types. Is that correct?
Yes, it's correct.
Okay. What exact meta information are you extracting? Are you extracting the same thing that the compiler provides?
Not exactly. No. For example, packed array, we don't care. The type specifier packed array, we don't care. We just need that it's an array. We don't care if it's a packed array.
So what you need to define very precisely is what information, what structure do you get out of that compiled function that represents the type information you need? Okay, and so you probably, I'm sorry, what?
Array rank.
No. I don't want you to tell me that. I want you to tell me how it will be specified here, right? In other words, I want you to tell me a structure that you can extract from this compiled code function that will probably be some accessor of the compiled code function, information of compiled code function, comma, something or other, that is exactly what you need.
It's exactly that. It's information of the compiled code function, comma, signature.
Okay, no, but not okay. Comma signature, is that right?
Yes.
So it's exactly that.
Yes.
Exactly that, right? Nothing more, nothing less.
Mm-hmm.
Is that correct?
What do you mean that? Exactly what?
Well, in other words, you have two things that you're getting from the compiled code function. One is its actual operation, takes certain inputs, gives an output. And the second thing is the output of information, compiled code function, comma signature. Is that right?
Yes.
Okay, that is it. That's everything you need.
Well, are you sure, Matteo? Because signature, it has the rank and everything?
Yes.
Okay.
Let's take an example here, okay? Give me an example compiled code function.
Well, you can just run the first cell there.
One.
Function compile, that guy.
This is just a joke, how long this takes.
Well, the very first time it takes...
I'm well aware of how it works.
Fine.
Thank you. Okay, why is there nothing called signature here?
I'm not in charge of that.
Okay, so can you make sure somebody knows that? That's a bug, presumably?
Yeah, I got it.
Okay, so how is this correct? Why does that not have a type wrapper around it? Okay, this looks like a hacky thing that wasn't documented, right?
No, it doesn't have a type. Okay, typed wrapper, sure.
Yes,
it probably should have a type.
It's wrong. Okay, so let's discuss this for a second. I believe this was not documented. So can you please confirm that?
Steven, this is another This is another meeting. This is another topic. I mean,
no, but I'm trying to understand exactly what you're using from here, right?
Okay.
And you're telling me, and if you use some undocumented feature of the compiler, it's not going to go well. So let's make sure that it gets documented. And I don't want to find out there's a big trauma because they fixed this to be correctly designed, and then all your code breaks.
I am checking argumentation.
Okay, all right, fine. So I think that's wrong, so that should get fixed. Okay, I get it. So you're using these two things. All right, now let's see how you use them. So you have a forward function, a backward function.
Sorry, it is documented. It is documented in function compile.
Okay.
If you look for
where is it documented? It's not documented. Documented means it's described at the top. I'm not interested in the fact that it's been stuffed into some random example.
But it's okay.
It's
not documented. Let's not talk about that anymore. It's not for us. It's for compile people. We have a lot of things to talk that are not about compile, and I think that's what we should talk about. Otherwise,
okay, fine. Let's keep on. Keep going. Yeah. But please don't tell me it's documented. It's not. Okay. So Devin, can you please go make sure that that gets done, but it'll need a review because it's obviously not designed correctly either.
Yep, I got it.
Okay, let's look at this. All right, forward function input goes to output. Backward function takes 3 arguments, apparently.
Yes. So it's a thing that basically compute the input gradient, given all that stuff.
Okay, so is this, can we do this? The automatic differentiation by default.
We've met with Rob Knapp today, and it seems that we'll be able to do it in the future. He's working on something.
Wait. What exactly are you saying? Are you saying that given a compiled code function with all the things the compiled code function could have in it, which includes all kinds of wacky, functions, special functions with branch cuts and who knows what else, we can do automatic differentiation of those? It seems very implausible to me.
Not in every case, of course.
Okay, so then explain to me what you mean.
I mean that.
Okay, you mean that sometimes we might be able to do it.
In the long run, there will be some fraction of cases in which it will work, and sometimes it will say, sorry, I could not automatically differentiate this.
Okay, so let me understand what the top level functions that do automatic differentiation look like. If I'm not mistaken, we could take a function and we could do automatic differentiation on it, right?
Yes.
Okay. Do we have that code?
It's not in production yet.
Okay, but you have that code. So you can take a function and you can generate from it an automatically differentiated version of that function. Is that correct?
Yes, a function which gives you the gradient of the first one. Yes, that was the claim.
Okay, right. Okay. So then we need a function called automatic differentiate or some such other thing, automatic some such other thing, which takes a function here and returns another function, right?
It also takes it takes another.
It takes the input.
It's the output gradient, basically, which Rob Knapp was calling it.
No. I'm saying it does the automatic differentiation. So it may have to take some additional arguments to say what it's differentiating with respect to, although I doubt that because I think the function.
It also takes another array. So basically,
it could be an argument of the output function as well. It depends.
Yeah. So, but anyway, you need it's more general than that. That is basically
okay. But so that function, we need that function because that function is the function that you are implicitly calling internal to compiled layer in the case where the second argument is automatic. Absolutely. Unless we have that function explicitly, it will be toast because if we have that function explicitly, people can check, does this function automatically differentiate? Right? Otherwise, it's totally bizarre. You're feeding it into compiled layer as a kind of a throwing a dart and seeing whether it happens to work. Right?
Yeah, of course. I mean, if the automatic differentiation fail, compile layer will tell you.
No. I'm not interested in that. I'm saying we need a function that will do automatic differentiation. You give it a function, it produces the automatically differentiated function.
We need the functionality, yes, of course.
No. We need that function, not just the functionality. We need that function, right?
Okay.
We're not just putting it in as an automatic hack inside compiled layer.
Of course not. Yes.
Okay.
Course, yeah.
And that function needs to work on top-level functions as well as compiled code functions, right?
That's not really for me. I will not be developing that. Everything we cared for.
I don't care. We're talking about design. I'm telling you from a design point of view, this function needs to work on top-level functions as well as on compiled code functions, okay? Now, I think you're going to tell me that you need more meta information about the function to be able to do this. And that's where we have to worry about what do we do in this automatic differentiation thing with respect to that signature thing and so on, right? And that's why it's going to get a little tricky. But we need to resolve that because that's necessary for this design. We can't have something.
Steven, I don't think it's necessary for this design.
I agree, Matteo. I agree with Matteo. I don't see in the workflow how it's useful. Look, you compile layer, compile function automatic.
It's going to go wrong. It's going to go wrong.
It tells you something. It tells you it cannot do automatic differentiation.
No, it's going to go wrong. It's going to be a throwing darts thing. It's not going to work in practice.
But what is I don't understand.
Okay, the reason I'm saying that is it is not a good idea to have something. There's a piece of functionality that is being used automatically here. It is automatic differentiation. That is a piece of functionality. It's a factored piece of functionality, right? Now, you are implicitly calling it as part of some function that does a whole bunch of other stuff.
Yeah.
Right? It is wrong to not factor it out.
Okay. No, I think it's a cool thing to have. I think the automatic D is a good thing to have. It's going to be useful. I completely agree.
Okay, fine. So let's understand, because I think there are going to be some bumps in designing that. And I want to understand those because I think those bumps are going to bite us in compiled layer if we don't deal with them first in automatic D.
What Rob Knapp is working on is,
Okay, is he here?
No, I don't think so. But it's
can we get him?
It's not something that is just intended to be used internally for us. I mean, it's of course he will expose that.
Honestly, we have a lot to figure out. This is sim side,
Okay, so listen. Look, I'm telling you, you need this function. You need to figure out with Rob a proposed design for this function. Once you have that proposed design, most likely it will just be compiled layer, automatic. Although it might say compiled layer, automatic D, I have no idea, that does this, okay? But I understand this idea. So what does this mean? The backward function takes the output. What does that mean? It takes the output.
It's the output of the layer. So you have a layer with input, output. Okay. And the arguments are, it is more convenient. We could actually recreate the output by calling the forward function, but
no, I think it's not a good. Well, but again, we need to understand this because automatic D will produce a function which has the same argument structure, right?
Yeah, I think it could produce many functions. One could just be the gradient, something that this is backward
function. So this is a particular choice of backward function produced by automatic D. So
wait. This is a good point. We should basically. So we have put that output argument there because, since right now the user is supposed to implement that function, and it might be useful to save time and use the pre-computed output. Sometimes you need it. You want it. But what I just said is when you do automatic differentiation, the result will not have that second argument. It has no idea about that. So what we should do is that, and we already evaluated this with Etienne, we should reverse the second and third argument of the backward function and make the third argument optional.
Yeah, I don't know. I'm not sure about that, but I think either way, you're going to have to end up with some kind of curry weirdness from that automatic D to get this thing. That's why I'm telling you, you've got to design automatic D. Okay, then all of this will be clear once you've designed.
But everything we care about that is that process produces another compile code function. And
I understand, but it has to be one with the correct argument structure.
Of course it is. It's the child of the function we're differentiating. Of course it is.
I understand, but automatic D, does it take arguments, right? Is it F prime is automatic D essentially F prime? If not, what is it?
It's F prime. It's a tensor contraction of F prime with another tensor.
Okay.
Which for us is the output gradient.
No.
Yes, it is.
You see, but I understand. I understand that that's what it is. But this is when you have. That's the whole point of factoring this automatic D thing out.
Automatic D will be more general. Us, we have a specific case, and we know exactly the case. It's minimizing a loss function. This is called automatic differentiation, not backpropagation. In our case, it is backpropagation because we are differentiating a function that has only one output, the loss. So we always go from the loss to the bottom. It's always
until you end up with something which has two loss functions, which sometimes happens.
Yeah, okay, it's two, but
you combine them, you sum them, you take some weighted average. So
well, I understand, but I keep on telling you. Okay, look, just design automatic D. It will be obvious what to do if you have that design.
Yeah.
Okay. And I think it isn't. This isn't. This is probably close, but it's not quite right.
All right.
Okay.
So this we already saw. So port naming.
Okay. So this is So this is something purely for the compiler group. This has nothing to do with you.
Exactly.
It has to do with supporting structure.
We ask them provide us a way to
Okay, but that's not going to be it.
Yeah, maybe not. Actually, I don't know.
No, that name is not the right name.
Okay. I just wrote that as
obviously that name isn't the right name.
I think it's
you have a function called tuples that does something completely different.
Sure. I mean, we
okay, so it's not the right name. So I mean,
we agree.
We don't want to propose a name for that. We
whatever it is, combined type or something. So I understand, but you're trying to do a design review and you're showing me things that are just obviously wrong. So, okay, we agree. This is going to be done by the compiler group, which for some reason is not represented here. Okay. All right, let's keep going down here. Oh boy. This
is for us, input port, output ports. So that's a way to specify names or shapes or both for the ports.
I understand, but let's understand what the actual function. So normally, what we've done, which has become something of a hack tower, is we have, so our normal way of dealing with named arguments, named inputs, named outputs, is with associations. But in the neural net framework, we have a slight weird side generalization of that. So, in this case, what is this actually doing? This is saying the previous layer was generating what amounts to an association containing port 1 and port 2, right? And that is going to be packaged in a certain way to be fed to this compiled function. Is that correct?
Yeah, so define so you can use this compiled layer by giving an association.
Exactly.
When keys
right, but but the bottom line of what this weird input ports function option would be, and it shouldn't be an option, right? This is the thing that is taking whatever is coming from the rest of the net flow, so to speak, and packaging it in the form that is used by the function inside compiled layer. Correct?
Mm-hmm. And to refer to this port, to do net extract, to do a bit of primary, say connect this port to this port.
Wait a second. What do you need to do for that? This is so. Is it the case then that you could? I thought this compiled layer was just a blob of LLVM code. It is not something where you can ask information questions like what are the weight values for this or that thing.
No, it is. It is because it's a citizen of the framework and it has all the properties of the other layers.
How can that possibly
ask for the shape? You can ask for the shape.
Okay, wait. Well, but you can't ask for weights, can you?
Well, that's
another story. That's another story.
Right. It doesn't make any sense. Right.
In principle, we have a design to add weights to this compiled layer.
But that's another story. I think
it's another story. It's not relevant to this. That's something where you might have meta information, and again, the compiler tooling framework allows you to store meta information, where you might store some meta information about the weights possibly, although that sounds complicated to me because the weights are either in compiled code or they're not in compiled code.
But we shouldn't be using compiler structures for that. This is a citizen of the framework, and the framework already has those concepts built in. Every layer has a as ports with names.
No,
and
wait. I'm not talking about the ports. I'm talking about weights. I'm talking about other information
layers,
things.
Yeah, layers also have
layers weights. Can have also weights inside.
Weights.
Okay. So what I'm saying is, the things that information supports for layers, only some of them are supportable for compiled layer, and that's okay, right? One of those. Right?
Yeah.
Okay. I don't exactly know by
Let's
heart.
Continue. Yes.
Right, because you can't get weights out of a piece of LLVM code.
No. Doesn't make sense.
Right. Okay. So in this case, what you're doing is, this is essentially providing wrapping to whose goal is to take the structure that is coming into this compiled layer and package it up so that it is correct for this internal function. Okay, so in other cases, there are other net layers that don't know the shape of their inputs and so on. Is that true or is that not true? Does every other layer in its very nature define the structure of its inputs?
Threading layer, you have you don't know how many ports you have. And we have the same, by the way, the same option will be used in threading layer and in a few other layers, which I forgot the name. Template, placeholder layer will be using that.
What is placeholder layer? So this is saying, okay, so option inputs arrow n can be used to fix the number of inputs.
We want to remove that. We want to remove that and use input ports.
I don't think we should call it input ports. I don't think that's the right concept, right? So what you've got here is, and you've got a couple of different uses here, right? What you've got is essentially a specification of either arrays, homogeneous arrays, or associations, right?
Homogeneous, no, they're different length, huh? It's a list of shapes, like port 1 is a 3x4, port 2 is a 2x3.
Okay, that's fine.
That's fine. It's list of dimensions. I
understand, but in a sense, what you're doing here is you're defining what are the possible part numbers. You've been given a blob of stuff as the input to this layer, right? This is defining what are the conceivable part numbers in that blob of stuff, right? The association specifications, the range of indices, of numerical indices, etc., right? Okay, so as I understand it, right now, the top level can be a named port, or it can be, in this case, right, so you've got these cases here, right? Except that to be more realistic, we could do something totally weird like that, couldn't we? Or could we not?
Yes. It just uses automatic naming for the names you don't provide.
And the automatic naming is numerical by position, is that correct?
Yes.
Okay, so let me just try to understand what this is. So, and this has been used elsewhere in the framework. This is the mechanism by which, in a sense, every neural net layer is given some structure. That structure might be a thing that says port 1 arrow, and then it might be a, whatever it is thing, whatever, some shape here. Or it might say, in general, this is the same kind of stuff that you might put into a data set, right?
Yes.
In principle, even the lower levels can be associations. Is that true?
No, at lower, you mean internally?
No. Well, it's only arrays. So it's just
okay. So currently, although that may not survive, in general, we could have something which is the same thing as the innards of a data set. That is mixed lists and associations.
One day.
Okay.
Yeah.
So the issue is that we do not have a generalization of dimensions for the cases that we're describing here. Right? We don't have one for this case here, and we don't have one for this mixed. In other words, if you say, what's the shape of a data set?
It's a tough thing, huh? It's a tough problem.
Well, let's
have a language to.
It's
interesting.
right.
Yeah. Let's go on.
So what it is Okay. However, the compiler is going to need that if it doesn't already have it in some way, because it needs to know the shape of everything it's dealing with. It is not a shape-shifting, not lizard, but piece of code.
It needs to know the rank, not the shapes.
Currently, yeah. I mean, yeah, the way it works is you see, you just have machine integer 1, machine integer 3. It doesn't have to have the exact shape, just the rank, the number of axes, number of levels.
Say that again?
It's just a number of levels that it needs, the compiler. The depth.
Well, but
array depth.
Okay, I'm not sure that's necessarily correct. So it doesn't need to know the explicit dimensions, is what you're saying.
The compiler, no. This is just for us to do inference on the network. And
although the compiler needs a different thing, which is it needs to know what the final types are down at the lowest level.
Exactly.
Yes, exactly. Final types and array depth.
Okay, but here now, do you always need to know the actual, or can one of these be automatic? Can the lowest level depth in some? I thought in some layers,
yes.
the lowest level depth.
They are. Yeah.
Okay,
like
so
linear
how do you
layer.
Specify that? Do you specify it with an automatic there, or you just specify it in a different way?
Yeah, no, you can do automatic means it's a specified.
Okay, but is that the only specification you can give for that case?
It's either well,
it's variable as well.
Exactly, you can use variable length, which means.
What does that mean?
That means
sequences?
that.
How do you write it?
It's a string called varying, or a string.
Oh my God! Okay.
Yeah,
okay.
But this is something that is, it's a hack, but it's also you cannot do it at any dimension.
Yeah, you can only do it at the first dimension, correct?
And you can put it only once. You cannot have like varying.
Okay. In the model of design in which the question is in which you have a boat and the boat is gradually taking on water, this is a time when you really have to start up the pumps in a very industrial way. Okay, we need to actually figure out how to do this design. This is a mess.
I mean, okay, you're talking about future things like we don't need to handle nested association.
No, I understand that, but okay, here's what I think. I think in the discussion that we were having about insertion and array reduce and all those kinds of things, right? We had this concept of a what was this concept? The concept of gosh, what is the idea here? The thing we were discussing about named mapping onto, how did this work? This is, I think this is the same idea. I think this is related to that idea. And since I can't completely remember what we had figured out,
like the name levels, things like that.
What's that? Well, yeah, but I mean,
naming levels, or
yeah, right, exactly. That's what it's about, naming levels. Right, the generalization of association that allows you to name levels. I think, okay, this is a related question, I think. Maybe not, but it's, I think it's, I mean, look, what this is a way to generalize dimensions for these more complicated structures. And again, it's exactly what you need for the compiler.
Yeah, it's extension of the type system. That's something I need as well for my data processing thing that we use for automatic machine learning. And
right,
in many places, yeah, in dataset, there's in a lot of places we have recreated this type system and
right, but I mean, so this is a particular need of a generalized dimensions that can represent the shape of something. Now, what you're going to do here is what you're saying is, this is the shape that's coming in, right? This is the shape to expect. This compiled layer expects this shape. Now, what is not obvious to me is that shape has to be repacked into the raw shape that is going to be fed to the compiled function. Is that true or not true? In other words, either there are two possibilities. Either the compiled function has a type declaration that represents this shape, in which case, then it has that. Go ahead.
It has. I mean, you don't specify shape. You don't just specify the depth, and that's it. So we are not contradicting what we say to the compiler. We're just adding extra information.
I know, but so that information should be addable in the structure that represents. In other words, when you say I have an array, I think we already have a mechanism for saying I have an array of length more than 3. We certainly need stuff like that. I mean, we have some of those mechanisms. And so what this is doing is we say we have an array which is concretely of length 3, for example. See what I'm saying? And I think that should be part of the type specification for an array. Right? You can say it's an array of arbitrary length, or it's an array of this specific length. And I believe there is already a mechanism for doing that. Okay, so I think whatever this is, you're saying, but the declaration in here does not need to be as specific. It doesn't need to know it only needs to know the depth of the array, not the size of the array, correct?
Yes.
That's what you're saying. Okay,
yes.
But nevertheless, in this, so what you're saying is you could have a generic, you could have something generic. Yeah, Bob is commenting, it sounds like a dependent type system. We have a very elaborate dependent type system. That's what all of these kinds of constructs are about. But yes, this is actually something a little bit beyond what's normally done there. I mean, the problem is, look, yeah, the problem is the type system rapidly becomes universal, at which point you can no longer do type inference because you don't have decidable results in it, et cetera, et cetera, et cetera, et cetera, et cetera. So it's a complicated issue of how you have something which is both broad enough to be useful and not so broad that you can't do type inference anymore. Or that you have something which we have had trouble with, where the type inferencer is a giant piece of theorem proving code, basically. This is like the, anyway. Okay, all right, so let's go back to this. So what this is doing is, inside the compiled function is a type specification. Now, you want to, like a cell exposing, various molecules on its surface, so to speak, you want to expose certain aspects of that internal type information at the level of the layer without going into the internal compiled function. Is that correct?
Yes.
Because this information will almost all be replicated in the type specification for that internal function. Is that correct?
Why replicated?
Because you have to tell it, this information is telling you what shape to expect for the compiled function, is it not?
They don't overlap exactly.
Why not?
For example, in the compiled function, you care about real 64 versus real 32, okay? But at the layer level, you don't. There's only reals. And in the opposite direction, at the layer level, you care about the shape.
Okay,
but for
this is a mess.
Function, you don't.
Yeah, okay. But that's not a reason to replicate the information twice, right? You're saying that there are slight differences in what is relevant to declare. I mean,
we're not replicating, we're adding information. Huh?
No, but you have a structure that has a lot of the same information in it, but what you're saying is the compiler. Okay, so here let me summarize. The compiler is more specific about the types, saying real 64 instead of just real.
Less about the shape, yeah.
And less about the shape. Not shape, but actual dimensions, concrete dimensions.
Yeah.
Right.
I agree that some information is duplicated, but this is separate systems which were conceived by separate people.
Don't give a damn, Matteo. I don't give a damn.
That's not the right argument. The right argument is that input ports, output ports are not made for custom compiled layer only. It's made for all the other layers. So this is just come up in this meeting because that's kind of the first time we went to here. But we had this same thing for anyway, a bunch of other layers.
Okay, so essentially what you want to do is, this is another type system, basically, that is saying what shape of thing to expect for this layer.
Yeah, I mean,
because you want to know that at the time where you're setting up the network, right? If it wasn't for that, you could just do it on the fly, and you just see what you get and set it up. But you need to know it at the time when you're setting up the network, because you need to train the network.
Sometimes you need, sometimes you don't. By the way, we already have that with just input. So if you get a linear layer, you can specify the shape of the input.
I know. It's always been very confusing to me. I mean, this input and output as strings is our mechanism for doing.
It's actually port names. I think we shouldn't see it as input output, just port name. It could be full bar. You specify the port, and you
so that's a different mechanism than what you've got here. Here you've put the input ports in a list,
and you can change the name. Yes, you can change the name. That's why I put a single argument case. You could also use that to just rename the input port of a linear layer, for example.
Okay, but I'm okay. So look, what we're doing right now is, if we say something like linear layer, right? What we say right now is input, arrow, and then the shape, basically. Is that correct?
Yes.
When I say shape, I don't really mean shape. I mean actual dimensions.
Dimensions, yeah. Dimension.
Right.
You could also put in net encoder. You can put,
What can I put there? A net encoder, which...
You can put a net encoder.
And what does the net encoder say in terms of shapes?
It has well-defined shapes depending on the settings and the type of the encoder and blah, blah, blah.
But wait a second. So this thing here stands for something which knows that it will return a 4x5 array. Is that correct?
Yes.
Okay. All right. So right now what we're doing is we are putting into the layers directly port numbers, port names, and their shapes.
Yes.
Right? Okay. So
but
the
it's not defining port names. This is not defining port names. In that case, linear layer already has a port called input.
I understand. It knows about that port. Exactly. That is one of its that's basically just filling in that argument.
Yeah.
Okay. So okay. Let me think about this for a second. So what you're saying is, and what's this? Could have weights inside the layer. Wait a minute. So this layer, I see. This layer might have parameters. How would the parameters entwine themselves into? I mean, the obvious way to do it would be that one of the arguments to, the arguments to the functions here are partly rapid change, actual running on actual data, and partly slow change, learned.
Yes.
Learned functions, right?
Yes, you see the signatures there. Forward function, now there is an additional argument, which is called weights, and also for the backward.
So this is one possibility. The other possibility is we don't change anything, and we define weights as we do in net function with net array layer. So basically, it's an input, as any other input of forward function and backward function.
Yeah, I understand.
And there's a little bit of technicality if we do that. Maybe a little bit more.
All right. So listen. We need to wrap this particular meeting. So look, let's summarize where we're at. Okay. First, you've got to learn about this compiler tooling things. Okay. Second of all, we've got this weird thing here, which is going to require another discussion. Next time, let's make sure we have the compiler people and Rob Knapp here, so that we can have a real discussion about this, and also about the actual automatic differentiation mechanism. Right?
All right.
So, I mean, is there something you're trying to get into 12.2?
Well, input ports, output ports. I think that's the main. And actually, I mean, compiled layer.
Well, right.
It will be experimental and everything.
This has got several more hours of work to do on it in terms of design, and it needs to have the right people. This is not one of these cheap design type things. It's going to be somewhat complicated. I mean, in the end, we may be able to have a design for this. It will not look like this, but it may have something which is, you know, basically the equivalent of this. But, you know, we need to know where it's going before we can elide it down to whatever it is that is the convenient syntax. And, you know, for that, the main thing is specifying generalized dimension type constructs. And for that, it will be useful to know both the compiler type specifications and the data set type specifications, which are not exposed, but they may have something useful in them. Does that make sense?
Yeah.
Sorry, I mean, this wasn't.
I was hoping it would go easier.
Yeah, well, so was I. I thought I could be late for this meeting because this meeting would be like 10 minutes and we'd be done.
Yeah.
Sadly, not so. All right, get another thing on the calendar, and we will continue. Right. We will solve this. And in the end, hopefully, yeah, Ethan is commenting that function compile can't compile to GPU code. I don't know. Again, we don't have people from the compiler group, so I don't really know the answer.
Yeah, at some point it will. Like the function compile, the idea is to have it compiled to CUDA. Now,
and there shouldn't be a fundamental problem with that, because the LLVM, that's a back-end LLVM code generation problem that, you know, is being solved elsewhere. Mm-hmm. All right, for people who are on this live stream, we're actually going to go to another live stream in just a moment here, talking about a utterly different subject. Oh, geometric scenes. All right, so, all right, to be continued. Let's get another one of these meetings in the next few days, and we'll come up with a good solution. All right,